Hello everyone, welcome to another Excel tutorial video. In this video I'm going to talk about the intercept term in regression as well as the concept of perfect collinearity and why we need to avoid that when running regressions. So to talk about the intercept term in regression, I have loaded up a simple data set of two variables we'll call x and y. And on the right, you can see the graphical results of a regression of y on x. So first, the green dotted line is our regular regression line that you can see fits this data quite well. This line is of the form beta naught plus beta 1 times x. So we have an intercept and a coefficient on x to give us the best prediction possible for y. I'm going to run this regression real quick in our usual way. So we can see that I've selected y as our dependent variable and x as our explanatory variable. Let's take a look at this. Okay, so what we've done here is estimated the intercept as 4.48 approximately. Now remember, the intuition behind a regression is that we're trying to figure out what number can we multiply by x to best describe y. Well, we're actually also doing that with the intercept. You can think of the intercept as just another variable in the regression, but it's always 1. We're trying to figure out what number to multiply by 1 to help us best describe the data. Now, we can go back to the data and actually run a regression where we drop out the intercept by clicking this box here that says constant is 0. Now we can see that the regression forced the intercept to be 0 instead of 4.48. And that, of course, affects our estimate for the coefficient on x. We can see that that has gone up significantly from before. Now, if we go back to the graph, that line is represented by the red dotted line. As you can tell, that does not fit the data as well. So generally speaking, setting the intercept to 0 is not a very good idea. We can illustrate my point that the intercept term is essentially just a coefficient on the number 1 by adding in a new variable that is just all 1s. And we can run another regression where we keep the box constant is 0 ticked, but now we change the input range to be our new variable c along with x, and then make sure that y is still the dependent variable. Now I'm going to run this regression. Now we can compare this with sheet 5, which had our original regression. We can see that the estimates for both coefficients are the same as before. The topic of perfect collinearity has come up a couple times, but we haven't spent much time on it yet. What this essentially means is that you can create one of your variables using a linear combination of some of your other variables in the regression. So to illustrate that, we'll make a simple linear combination of x. So we'll call this one z. And let's just say we make z equal to 2 times x. So remember that we can create z by one of our other explanatory variables. Now let's try to run a regression of y on both x and z and see what happens. verify that our y range is still correct, and our x range is now including both x and z. We're going to uncheck this constant is 0 box. We're done doing that, and run the regression. Now, as you can see, we have a problem. We couldn't get any coefficient estimate for x, but we did get one on z. Now let's compare that with our original regression. We can see that the estimate is exactly 1/2 of the coefficient estimate on x, and that's because z is simply 2 times x. Now, why couldn't we get any estimate for the x coefficient? Well, remember that a regression is trying to give us the coefficients such that we best describe the data. But since x and z are really the same thing, just one is twice the other, the algorithm has no way to decide which of these is actually explaining why, because they both do exactly the same thing. So we need to just get rid of one, and Excel chose x to drop. But we could easily have dropped z as well and gotten our original regression result. Now, the reason that I started this video talking about the intercept is simply to point out that the intercept, because it really is just another variable, just all of the values are 1, that the intercept can also be used to create perfect collinearity using a linear combination. Now let's redefine z as 2 times x plus 3. Now remember that 3 is simply 1 times 3, so this is still a linear combination of x and c. So for example, we could really put this in that way. I'm going to fill this out and run the regression again. We can see now that x has still been dropped because x and z are perfectly collinear. Since z was still based on 2 times x, the coefficient on that has not changed, but what has happened is that the coefficient on the intercept has gone down because we now added 3 onto z. So that variable is taking up some of what the intercept did. Now let's look at some of the practical implications of perfect collinearity. We're going to go back to our ACS dataset that we've been using in these videos. The most common way that you can accidentally create perfect collinearity is when you are creating dummy variables. So in a previous video, we created a dummy variable for female. So let's do that again. Remember that in this data set, a 2 in the sex column means female. So if that equals 2, then we're going to say 1, otherwise 0. So 1 for female and 0 for male. Okay? And we ran some regressions using this variable. Now let's say that I also create a male variable that's doing the same thing. We notice that male and female are perfectly collinear. Why is that? Well, we can use a combination of female and the intercept, which is a variable that is all 1s, to create male. We can demonstrate this by making a new column that is equal to 1 minus female. And we can see that we've perfectly replicated the male variable. Now let's try to run a regression to illustrate this. We'll set total income to be our dependent variable, and we'll set male and female together as our explanatory variables. And we can see again that Excel automatically dropped one of our variables. Note that since male, female, and the intercept term are all linear combinations of each other, we can choose one of them to drop. Now, normally we would simply drop either female or male and have the other as the baseline. But you could also drop the intercept if you want. So let's try that. We'll run another regression. But now I'm going to check constant is 0. And we can see now that we have estimates for both female and male. So what this regression has done is simply calculated the average income for females and the average income for males. But the reason that we don't usually do this is that we are now comparing the female income with 0 and the male income from 0. And clearly those are going to be statistically significant unless our data set is very small. But that's usually not what we care about, right? We usually care about the difference in treatment. So we often want to know, what is the difference in male and female income, and is that statistically significant? And this regression does not directly get at that. What would directly get at that is if we ran the regression where we drop one of the dummy variables. So let's just leave in female for now. Uncheck this box to let the constant be positive, and run this again, and we can now see that the average female income is a bit lower, and now this t-statistic will be directly testing whether that is a significant number. So just keep this in mind when you are constructing dummy variables, that you always leave out one group as your base case. So if you were doing dummy variables on race, then you would choose one of these to be your baseline, and you would only make dummy variables for the other categories. That's all I have to say about perfect collinearity. As always, if you have any questions, do let me know. Thanks for watching.